All right. Thank you. So today I want to speak about the construction of these Galois representations, or at least give some ideas. So I guess if you want more details, you should book a flight to Berkeley. We program at the MSRI, a week-long program with the goal of explaining in more detail what's going on. So let me first state the theorem that we're after. So let's take, well, slightly more generally than the previous lectures, any totally real OCM field. CM meaning it's a quadratic, totally imaginary extension of a totally real field, and any integer at least 1. And so we're working then with the G group GLN over this field K. And so the theorem is that for any system of Hecke eigenvalues, appearing in some homology group of the locally symmetric space corresponding to this group GLN over K with coefficients in Fp. That will be less precise in the previous lectures. There exists, so let me call this system alpha of Hecke eigenvalues. There exists a representation rho alpha, which goes from the absolute Galois group of this field K to GLN Fp bar, such that for all p not dividing p times the level, it's a level referring to some level that I didn't specify here for this locally symmetric space. The characteristic polynomial of rho alpha of a Frobenius element can be described in terms of Hecke eigenvalues. So this representation is unramified outside p times the level, and there you can get this description. Okay, and so to simplify matters, I will today concentrate on the case that the base field is just irrational numbers. So yesterday I was explaining the case of GL2 over an imaginary quadratic field, and now I'm doing GLN over Q. And I guess the interesting case is when this integer n is at least 2. Because for GL2 over Q, I explained in the first lecture that matters are not so hard. And so for a reason that will become clear in a second, I will also denote this integer n by G. And so let me first explain a bit about what was known before about the existence of Galois representations. And in the specific setup that I will eventually use. So for this, let AG be the Siegel space of genus G. And so thinking over the complex numbers, that's the Siegel space modulo a congruent subgroup gamma. So now gamma is a subgroup of the symplectic group. Congruent subgroup. So really I should include this gamma in the notation here, but I won't. So what is SG? That's the Siegel upper half space. So SG So that's those n by symmetric n by n matrices, so m symmetric. And the imaginary part of M is positive definite. And so this is the symmetric space for the group sp2g of R. And so thinking algebraically, geometrically, this AG, so you see that in this case, again, this symmetric space carries a natural complex structure because you have the complex numbers there, and this complex structure is preserved by this action, so it passes to this quotient. And in fact, it's again algebraic, so all AG are algebraic and defined over maybe a finite extension of Q. And you can identify them with the moduli space of principally polarized. The BM varieties with some level structure. And this is this interpretation as this moduli space, which shows that they are algebraic. Also, I should say that if you specialize to the case where G is 1, which we're not really interested in, but just to say this, so this is just the modular curve that we've looked at before. And then maybe I'm mixing up GL2 and SL2 at some points. But, and also, I should say that similar to the modular curves, there's some notion of cusp forms. And you also have some Heck operators. Okay, and in this situation, it is known that you can attach Galois representations to cusp forms. I will give names in a second, so let me first state the theorem. So let F be a cuspidal Hecker eigenform maybe of regular weight. So for the modular curve, you should think of the situation where the weight's at least 1, but yes, everything's holomorphic. Sorry. Then for any P and isomorphism between QP bar and the complex numbers, so we should think of this F really as being a complex gadget, but in a second I will write down something which is a QP bar gadget, and so for this I have to fix any isomorphism of these two fields. They are abstractly isomorphic. So there exists a Galois representation attached to it, so a rho Fp, which goes from the absolute Galois group of Q, and the group it goes to is GL2G plus 1 of QP bar. So it will actually be a self-dual representation. And it will have properties similar to this case. I won't write them down. So it's unramified outside P times the level. And at unramified primes, you can describe what the characteristic polynomials of Frobenius elements And so I should indicate I should say who the theorem is due, so it has somehow two parts. So the first part, I should probably mention the names Arthur and Go and Waltz-Berger. So in Go in particular for the proof of the fundamental lemma. So their work together shows that there is an endoscopic transfer. Well, for g equal 1, so that's some of the sim 2 of this representation you would expect. Yeah, and I mean, really hard. This is here. I mean, for g equals 1, it's well known, and the hard part is some of g is bigger than 1. And maybe g equals 2 is still not so hard because then you actually can find them in the cohomology. But for big G, you actually have to do something. So they proved that there's an endoscopic transfer from automorphic representations of the symplectic group to, well, I could say self-dual automorphic representations of, and now one might get confused, that's GL2G plus 1. So you should really think in terms of dual groups. So the dual group of SP2G is SO2G plus 1, which has a natural map to GL2G plus 1. And well, it's not so clear what it means for an automorphic representation, really. But there is a definition by Arthur where you look at certain L functions for wedge2 or sim2, and he shows that it's orthogonal in this sense. Yes, I mean, or yeah. I'm not exactly sure what is known about the orthogonality of these Galois representations eventually. I think people have studied this, and there might be results that show that the Galois representation you construct is actually orthogonal. So it should really map to some G spin group. All right. So that's the first part, that you can transfer this guy, which corresponds to an automorphic representation of the symplectic group, to an automorphic representation of GL2G plus 1. And then people have showed that to such gadgets one can attach Galois representations. It started with the work of Closer and Kottwitz, and then especially Harris-Taylor made a very important contribution. And then there were some remaining cases which were finished by Chin and Genevieve-Harris. And they show that one can go from self-dual. Maybe at this point I should also say cuspal representations. I mean, of any GL M effect to Galois representations. And so, as I already said, you don't find these Galois representations in the cohomology of this Siegel space itself, as was the case when for the modular curves somehow. But instead, you can find them somewhere in the cohomology of some Shimura variety. And it's a unitary group of signature 1 and minus 1. That one has to be looking at. So what one does is one takes a self-geocuspidal automorphic representation of GLM, base changes it to some imaginary quadratic field, and then descends it back to some unitary group of this signature, and then looks at what you see in the cohomology of this Shimura variety. Okay, and so the proof will use the existence of these Galois representations. And so, so we have this picture of a symplectic group, and I'm really interested in this general linear group, and so I have to explain how the general linear group enters the picture here. So that's the business of the Borel-Serre compactification. So that's a compactification of AG into this gadget. So remember that this guy was a complex manifold. And so it was even algebraic, but let's forget about this for the moment. Just consider it as a topological space. Namely, this Borel-Serre compactification will only be a real manifold with corners. So in this picture, we're somehow leaving the world of algebraic geometry. But it has a favorable property that J is a homotopy equivalence. Which makes it somehow very suitable for understanding. So AG is non-compact, compactified in this way, and because the inclusion is a homotopy equivalence, it's rather easy to say what the boundary contributions are. So the strata, this is naturally stratified of this Borel-Serre compactification, are parametrized by rational parabolic subgroups P in the symplectic group. Rational meaning that they're already defined over the rational numbers. And each stratum is a torus bundle over the locally symmetric space for the Levy and so in particular, you can look at the Siegel-Levy subgroup, so P, which is star, star, 0, star, where everything here is of size G inside the symplectic group. And so the Levy of this guy is just a general linear group. And so this means that in this Borel-Serre compactification, so at the boundary, you will see some terms which come from this locally symmetric space we're interested in. And so this implies that the torsion homology of the locally symmetric space GLG contributes to the homology of this Siegel space with FP coefficients. Well, you have a long exact sequence. So 2 terms are the homology of this of AG, and the other term is the Borel-Moore homology, and then the other term is the contribution from the boundary. Let's forget about the other boundary strata. They are easy to control by induction. And so then you know that it has to appear either in the homology or in the Borel-Moore homology, but then by duality you can move them into the homology. Okay. And so at this point I can state some of the key technical result. So at this point we somehow succeeded in, or the idea was suggested by Clausel, so we have succeeded in moving so this locally symmetric space didn't have any algebraic structure, but now we have moved this into the homology of some actually algebraic object, and so we're in, as an algebraic geometry, you think you are in a better shape now. And so the crucial theorem is the following. For any system, let's call this again alpha, Hecke eigenvalues in some torsion homology group, the Siegel space, there exists a holomorphic hospital eigenform F such that the Hecke eigenvalues of F are congruent to this system of Hecke eigenvalues alpha modulo P. I mean, you might more naively hope that for Shimura varieties such as AG, there is in fact no torsion inside of the FP cohomology, so that the integral homology would be torsion-free. In this case, you could simply lift this to a Hecke eigenclass in the integral homology, and you know that the integral homology is in some way expressed through holomorphic hospital forms, and so you would find such a form there. But the argument is much more indirect. So in general, there's still some torsion on the Shimura variety, but it's somehow not very substantial. So you can always lift it to characteristic 0 in this weak sense. Yeah, you wouldn't lift it necessarily to a cusp form. Yeah. Right. So that's somehow. So some of the theorem is doing 2 steps at once. So first of all, it's showing that any torsion, I mean, so the same theorem is true for any Shimura variety of Hodge type, say. And if the Shimura variety is compact, it simply says that all the torsion can in some sense be lifted to characteristic 0. But the theorem is also doing something else, namely if you have a classical Eisenstein series, it's also producing congruences between this Eisenstein series and the cusp form. In this case, you would consider a Shimura variety corresponding to a unitary group of signature 2, 2, for a quasi-split unitary group. So somehow over totally real fields, you work with symplectic groups, and over CM fields, you work with unitary groups. Eden. Okay. So let me first explain how, assuming this theorem, one can get the desired Galois representations. So that's the following diagram. So as I said, you start with a torsion homology class for this group GLG. Then using this boundary contribution, which is often termed, given the name of Eisenstein classes, you go to the torsion homology of the symplectic group. Yeah, I mean by torsion homology, I just mean with FP coefficients. And then by the theorem, you can do this lifting and end up with some classical cusp form. No, the weight might go to infinity, and also I might have to increase the level at P. The level away from P stays fixed. So what I can control about this form is the level at P and the weight. But I can ensure that it's of parallel weight somehow. So that it's a section of just, so on this Shimura variety you have the natural ample line bundle omega, which is the determinant of the Lie algebra. And I can ensure that it's a section of a tensor power of this line bundle. So you get to a classical cusp form in SP2G, and by this big theorem that I stated earlier, you know that from there you can go to Galois representation, which goes to GL2G plus 1, QP bar. Which I can then, of course, reduce mod P, so I get some rho bar, which goes to GL2G plus 1 of FP bar. And, well, now we're not quite there. So remember that we wanted some representation into GLG. Now we ended up in GL2G plus 1. So that's because somehow considering these Eisenstein classes, I moved to a bigger group. And because I'm on a bigger group now, I'm also getting a bigger representation. And so the final step then is to show that rho bar is really isomorphic to some rho 0 plus rho 0 dual plus trivial, where this guy is a sought after representation. And I mean, this final step is not so hard. You just have to do it. Yes, because somehow this torsion class was somehow had corresponded to some Galois representation which is somehow highly reducible. But then in this lifting I made some arbitrary choice, so I also get some kind of arbitrary lift, which will certainly not be reducible in general. But I should say that this main theorem I stated about attaching Galois representations to torsion classes So I stated it only over fp, but there is a version of the theorem where you do with mod over z mod p to the n z, and then finally in characteristic 0. And so, all right, so the key step is somehow to prove this lifting theorem here. And unfortunately, I can't really say anything about the proof, but I can explain what is the geometry that goes into the proof. And so I will explain now some geometric statements, and it will probably not be clear how they are at all related to the statement, but I'm sorry for that. So just to give you some idea of why I'm going this way. So note that in the theorem we demand a congruence mod p for f. And so we have to work with p-adic forms, i.e. over this ag, which a priori lives over, I said it lives over q, and so you can base change it to qp, p-adic numbers. And so this form f should somehow more naturally not be a complex form, but a p-adic form. And so that's why we're looking at these gadgets over qp. And so the proof relies on some new results. On the geometry of these guys. In a second, there will be a very big level at p. Yes. So, in fact, I will only explain the case where g is equal to 1. In the general case, it's very similar. It's just everything's so much bigger that I don't know. It's harder to explain. So, recall the modular curve again. So, m gamma, which was h2 mod gamma. Where I recall h2 was the complex upper half space. And so thinking algebraic geometrically, that's a modular space of elliptic curves with some gamma level structure. And so over the complex numbers, we have the following diagram. So you can take the inverse limit over all levels gamma of these modular curves at level gamma. And then I'm lying a little bit, but essentially you get back the complex upper half space. And so if you think of the complex upper half space in these moduli theoretic terms, and what this parameterizes are pairs of an elliptic curve E and alpha. So E is an elliptic curve over C, and alpha is the trivialization of the first integral homology with Z2. And I guess to just get the upper half space, I have to ask that this is orientation preserving. And so, just by its very definition, the complex upper half plane embeds tautologically into the projective space over the complex numbers. But what is this map in moduli theoretic terms? So moduli theoretic terms, you take such a pair E with a trivialization of the first integral homology, and you map it to its Hodge filtration. So how does this work? So why is this map alpha? Also the first complex homology is trivialized. And this projects naturally onto the Lie algebra of E. So Hodge filtration. So you get a varying one-dimensional quotient of this fixed two-dimensional vector space. And so what we want is we want a similar picture with the periodic numbers. With CP. Where I recall that CP is the completion of an algebraic closure of QP. And so in particular, we have to understand Hodge filtrations over this periodic field. So let me take X over CP, some proper smooth variety. And then, of course, you still have the theorem of Hodge, which says that the Hodge to de Rham spectral sequence degenerates. So sequence. It's an E1 spectral sequence whose E1 term are the Hodge cohomology groups, so cohomology groups of the differentials, and converging to the Rham cohomology. So this spectral sequence degenerates already at the first page. And so this means that there is a filtration on the de Rham cohomology group whose associated gradients are Hodge cohomology. And I will call this Hodge de Rham filtration. However, it turns out that this is not really useful in the periodic case, at least not for what we want to do here. So the problem is the following, that if you look at the Rham cohomology, then over the periodic numbers, it's not true that this is isomorphic to étale cohomology with CP coefficients. So over the complex numbers, you know that you can compute the Rham cohomology as singular cohomology with complex coefficients. But the same result is not true over CP. So I mean, they are vector spaces of the same dimension, but there's no canonical isomorphism between them. Well, I mean, QP and tensor. And so what we are trivializing in this tower of modular curves is the first étale cohomology of this elliptic curve. But we have a filtration only on this guy, and so because these are not isomorphic in the periodic case, we can't use this to get this Hodge filtration we're looking for. And for the experts in periodic Hodge theory, you would expect that there's an isomorphism after you tensor these guys to Fontaine's field B de Rham. But if you're only working over CP, not even this works, because there's no map from CP to B de Rham. So we do not get a filtration on this way. However, it turns out that there's a second spectral sequence. Namely, there exists what I call the Hodge-Tate spectral sequence. Which looks very similar, but has some very interesting twists. This time it starts at the E2 page, naturally, which is again just Hodge cohomology. But if you look closely, we'll see that I and J are exchanged. And also you have to put a Tate twist. So it looks a bit like the conjugate spectral sequence. And it converges to these groups we're looking. We want to have. So I'm putting a Tate twist here, which doesn't really say much because I'm working over an algebraically closed field. But if this guy was defined over some smaller field, then with a Tate twist, it would be Galois equivariant. And so this degenerates again at the first page, so this time at E2. And so this implies now that there's also a filtration on this guy whose associated gradients are again Hodge cohomology. Okay, so let me give an example for this or situation. So if E over Cp is an elliptic curve, then we have two filtrations. So first of all, we can look at de Rham homology, which you define, say, as being dual to de Rham cohomology. And so this is naturally filtered by the Lie algebra of E and the dual of the Lie algebra of the dual elliptic curve. So I'm implicitly thinking here also about the general case of an abelian variety where the same thing is true. And it's really important to write the dual abelian variety. On the other hand, you get a filtration on the periodic Tate module of E, which you should think of as a first integral homology with Cp coefficients. And tensoring this up to Cp, you get another filtration where this time this term is the quotient and the sub is canonically the first Tate twist of the Lie algebra. And so over the complex numbers, these two guys in the middle are isomorphic, and these exact sequences are canonically split. However, over the periodic numbers, both of these filtrations are just filtrations. Although, if this guy was defined over a smaller base field, the Galois equivariance of the sequence forces a unique Galois equivariant splitting. But the splitting exists only if this elliptic curve is defined over a small base field like QP, and not if it's defined just over CP. So we really just have a filtration. So let's get back to the modular curves. So fix some gamma. And so we want this map which parameterizes this Hodge filtration. And so for this, we have to trivialize the p-dictate module of E. But this means we don't have to go up all the tau of the modular curves. We only have to go up the tau given by the p-power congruent subgroups. So we call them gamma p to the m. So I guess it's slight abuse of notation, but so I intersect the usual gamma p to the n with my fixed gamma. So it's a gamma in this gamma. And so I look at these spaces m gamma p to the n. So they live over Q. And I base change them to my p-adic field Cp. But so in this case, this was really just a complex analytic picture. So this map didn't exist as a map of algebraic varieties. I mean, the upper guy is not even an algebraic variety. And similarly, in the p-adic case, we also have to pass to p-adic analytic spaces. So my favorite language for this are the adic spaces, but you might work in other languages. So that's some kind of p-adic analytic space. I mean, in the sense of Huber's adic spaces, if you know them. But yes. So they're actually locally ringed topological spaces equipped with valuations at each point. And so one is, in the adic world, one is keeping track of all possible valuations, even the ones of higher rank. And so the theorem that's supposed to mimic this diagram I just erased is the following. So first of all, it is possible to go all the way up the p-tower. And this again gives rise to these perfectoid spaces that appeared in the title of this lecture series. So there exists a perfectoid space that I call m gamma p infinity over Cp. So why is this a theorem? So the problem is that in this rigid analytic or in this p-adic analytic world, one always wants to work with convergent power series. So one has to take p-adic completions of all the rings that somehow appear in the business. And so in particular, one has to take a lot of completions in this business. On the other hand, as you go up this large tower, the rings you introduce are highly non-Euclidean. And so in the non-Euclidean case, completion is not so well behaved, so it's not flat anymore, etc. And so it's not a priori clear that you can get anything well behaved if you go up this tower and still want to work in some analytic category. But there is this very isolated class of spaces, the perfectoid spaces, which are well behaved although they are non-Euclidean. And it's some kind of good fortune that they actually turn out to be perfectoid spaces. So roughly the notion of perfectoid means that you have R some Banach CP algebra, and you have in there the power bounded elements And then the crucial condition is that if you look at the Frobenius, so you should think of these as, I mean, these are essentially functions bounded by 1. So it's like ZP inside of QP or something like this. Some integral structure on there. And so you can now reduce this ring mod P and look at Frobenius map. And the crucial condition is that this map is surjective. So this means that as you go up this P towers, many, many P's roots are extracted. So if you think in terms of integral models for this modular curve, it means that there are highly inseparable morphisms going on in the special fiber. Okay, so that's the first part, that you can actually make sense of this object at infinite level. And the second part is that now this period map actually exists. So well, the same result is true for any Shimura variety of Hodge type. The crucial input is the theory of canonical subgroups. So if you think about the modular curve and you think about the ordinary locus for the moment, then if you go up to gamma naught P level first, then there are two components in the special fiber. One maps down isomorphically on the ordinary locus, and the other one maps down via Frobenius. And so if I look just at the gadget which maps down via Frobenius, and I go up further, the gamma naught P to the n tower, then the transition maps will continue to be Frobenius maps. And this somehow accounts for this perfection. And one has to extend this from the ordinary locus to all the modular curve. And one first extends just to a strict neighborhood on which this canonical subgroup still exists. And then one can do the whole argument on the strict neighborhood. And then finally, at infinite level, the locus where everything is good is stable under the whole action of the group, and then you can move it everywhere around. There's a GL2 QP action on this guy. The point is that any elliptic curve is isogenous to one in any given strict neighborhood of the ordinary locus. Which I prove this also for Abelian varieties, and I'm not sure it was known before. But okay, anyway, so the second part is that there exists this period map which goes from this infinite level guy to P1, again considered as some analytic space. And so what this does is it takes an elliptic curve together with a trivialization of the periodic Tate module to or the Hodge filtration. So in this case, CP2 is now via alpha trivialized. So this guy is just this. And then we can project onto a varying one-dimensional quotient. Again, there is some subtle twist going on in comparison to the complex picture. Because on the complex picture, we projected onto the Lie algebra, but now some of the two guys are exchanged. So we're actually projecting onto something different. I only use the second exact sequence. The first exact sequence doesn't help in this case. A Tate curve gets contracted to a point. Maybe I can show you the picture. So I wanted to say two things about this map first. So yeah, this map is really extremely strange. I will come to this in a second. So first of all, it's GL2 QP equivariant, where GL2 QP acts naturally on this P1, because we're over a periodic field. And it's also equivariant for the Hecke operators away from P. With respect to trivial action on P1. So this means that whole Hecke orbits for the group away from P get contracted under this map. And it might be very counterintuitive that there are any such maps. Some of the reason that the sec operators away from P don't do anything is that we're only somehow looking at p-adic cohomology. And so changing by Poisson-Genier away from P doesn't do anything to the picture. And so in the last 5 minutes, let me just explain what this map actually looks like. So you have this guy at infinite level, and it's naturally stratified into two parts, namely into the ordinary part and the supersingular part. That's because the special fiber of the modular curve has a stratification, and then you can pull it back to the generic fiber and the specialization map. And so there's this Hodge-Tate period map which goes to P1. And there's also a kind of natural stratification of P1, namely into its rational points and the complement, which is usually called Greenfeld's upper half space. So this is P1 minus the rational points, and it's called Greenfeld's upper half space. And it turns out that this map is compatible with these stratifications. So this has a very strange consequence that if you somehow start at some ordinary point and then slowly go towards to the supersingular part, then the image will stay constant for a while, and then suddenly you will start to move. And I mean, this is something that's absolutely not possible in finite type geometry. It's something that appears in this infinite type world. And so what does the map do on the two strata? So on the ordinary locus, it simply measures the position of the canonical subgroup. So the canonical subgroup on the ordinary locus is a canonical one-dimensional subgroup of the p-divisible group, which gives you a canonical one-dimensional subgroup of the p-adic Tate module. And so if you trivialize the p-adic Tate module, it gives you an element of P1. And that's what this gadget gets maps to. But on the supersingular locus, something much more interesting is happening. So what happens on the supersingular locus? So what is the supersingular locus? So if you think about level 0, then in the special fiber you have a finite set of supersingular points, which gives you an open unit disk. Each of them gives you an open unit disk, so finitely many open unit disks. But as you go up this p tower, at each of these open unit disks you will get the Lubin-Tate tower. So this means that at infinite level, what you get is just a finite disjoint union of Lubin-Tate space at infinite level. But now there is this strange duality isomorphism, which was first proved by Faltings, that Lubin-Tate space at infinite level is actually the same thing as Greenfeld space at infinite level. And so what is Greenfeld space? So Greenfeld space is a that finite level, it's a finite état covering of Greenfeld's upper half space. And so again, I'm passing to infinite level here. But in particular, by its definition, it projects down to Greenfeld's upper half space. So this gadget is somehow pro-finite état over omega 2. And That's what the hot state period map does. So the strange isomorphism between Lubin Tate and Drinfeld tower is somehow built into the geometry of this hot state period map. And it also means that the fibers over this part, they are profinite sets, whereas over this part you get some whole curves. It's really strange.